Yeah.
You want to share your screen?
Yes. Okay, awesome. Cool. Yes, hello. As I just introduced, I'm Zachary Knudsen. I'm an outgoing undergrad. And so I'm here to talk about the model that has been developed here over the past couple of years at the CFA to model the joint or like model deconvolution of observations of Cygnus A, and I've applied it to Cygnus A. So first, a little bit of background on how the low counts imaging process goes, because we're working in X-rays, we have very few counts, and so you end up with a couple of different steps. So you end up with you observe some flux on the sky. Maybe it looks like this, or a galaxy or something. And then you convolve it with your point spread function. And this point spread function is essentially encoding, essentially has information about the like misalignment of the mirrors or diffraction from light. And so you also have to account for like the exposure of the instrument that you're working with, and also the fact that we are working with so few counts, you end up with a significant amount of Poisson. And so your final image might look like the right, which is significantly less useful than the left. The objective would be to just completely undo this process and get the recover the true flux from your counts image. However, there's some trouble with that. So I guess, okay, actually, in theory, the point spread function can be simply deconvolved if there is zero noise in your image. However, if you add even a little bit of noise, you end up getting essentially gibberish out. And so you need some method to model this deconvolution process. I guess a little bit of background on the Chandra X-ray Observatory. So we actually know what the point spread function roughly looks like. We can model it empirically, like as you can see on the left, or you can use faint point sources to model the point spread function, or you can sort of model the path that light takes through the telescope to arrive at a Mark's point spread function model. And actually, I'll pause for any questions. I realized like I'm kind of just talking.
It's okay. Don't right into the problem.
Sure.
There's from what I've heard, Chan, there's also a spectrometer. Is there such a thing, right? Okay.
Yes. So with every observation, and I'll get this. I'll get to this later slides. But with every observation, you are also recording the
energy of the
a proxy of the energy, of each of the photons.
So is the PSF must depend quite strongly on the energy, right?
Not strongly.
Okay.
It does depend a bit.
Okay.
So, for example, for Chandra, the PSF is narrower but blunter at low energies, and sharper and more diffuse, more wingy at high energies, but not spectacularly so. I mean, you could, if you approximate it by one, you're not going to do too bad.
Right.
Thanks.
So okay. Essentially, like what you can do. Well, I won't say simple, but like a way that you could model this deconvolution process is by calculating a maximum likelihood estimate. And so essentially what you're doing is that for each of the pixels, you have a certain number of counts, and then you're trying to recover the average number of counts that should have fallen on that pixel. And so for the astrostatistics people, this is the CHASC statistic, where D of J is the number of counts you've observed in that pixel, and then lambda of j of x is the mean number of expected counts in that pixel. For the astrophysics people, this is essentially just the Poisson likelihood of observing a certain number of counts, right? And so if you sum over all the pixels and you use some sort of minimizer or like a function minimizer, you can arrive at and you know, perform multiple iterations on your minimizer to arrive at or like your gradient descent model, or like you can arrive at a maximum likelihood estimate. If you take this to convergence, you end up with essentially something that looks like this. You end up with the diffuse structures in your image sort of being scrunched into little point sources, because you are fitting, or if you go like completely to the maximum likelihood, you end up fitting all of the noise in your image. And so you end up getting something that looks like this. And so what people have,
There's too many parameters in the model, so that the maximum likelihood is really overfitting. And
yes.
I also suspect it's a ridiculously multimodal surface.
Mm-hmm.
So if you started in a little different place, those peaks move around. So it's really unstable.
Yes, yeah. The likelihood surface, like near the minimum or the maximum, is very spiky. And so you'll fall into one of those little spikes and you'll get something that looks like this. What people have done in the past is to essentially stop early, right? You don't go all the way to convergence, and you can get something that looks good, right? But there's no clear convergence criterion. Like there's no criteria. It's by eye, essentially, right?
It's astatistical.
Yes. Yes. It's the statistics of the human eye.
Sounds like astronomy.
And so insert Jolly Deco. Jolly Deco adds a patch-based image prior to essentially tell the model that there are local correlations between nearby pixels. And so we use, for the statistics people, we use a Gaussian mixture model, which has been trained on the Gleam radio survey, or some of the images from the Gleam radio survey, split it up into patches, and then you train your Gaussian mixture model to try to find the primary components that make up those patches, right? And so this is some of those modes to the right. And so
Can I just point out that this is the same method that the black hole image people, the EHD guys used.
It's different data.
Well, radio data.
Red data in black hole.
No ducks.
No,
No
that's,
ducks.
well, we don't know.
and so essentially, what you get now is an updated likelihood calculation where you are subtracting off this prior term, where now the patches of the image will be compared against this Gaussian mixture model, and that Gaussian mixture model will give you a likelihood, and you subtract that likelihood from the total likelihood. And now we have this hyperparameter beta, which is just a multiplicative factor, which is user defined, which determines essentially the strength of the priors, right? Yeah.
Is this linked to shrinkage or penalty of for the frequentist aspect? Is this related or not?
Yes, it penalizes like inconsistencies, or it penalizes like these, right? And so things end up a little bit more smoothed out. For example, just testing out the model on this duck, the Jolly Deco reconstruction, at least to my eyes, does significantly better than the just simply smoothing the counts, which you might do if you didn't want to use some sort of a deconvolution model.
Are you using, when you do this, are you using the Glean library prior for your duck?
I'm fairly certain.
Just
Sorry,
because
it's been a
funny
year.
structures that you see in there may actually come from a prior for the priors for astronomy.
Yes,
So it makes
yeah,
sense.
it is,
Yeah.
it is either Gleam or JWST. I'm
But it's
pretty sure it's
astronomy
Gleam.
prior, that's
Yeah,
why,
yeah,
I think
but-
that's why you see some of those funny structures in there.
Yes. And so, yeah, we're able to reproduce some of the like finer structures. Obviously it's not perfect, you're working with noisy data, but significantly better than just the data itself.
Just out of curiosity, how much noise did you put in as a percentage?
It's Poisson counts.
It's a, yeah,
so
it's a,
what's the
Like
average?
how many counts were there per bin or something like that?
great question. I'm not actually 100% sure, because it was a while ago, that I made this slide in particular. It would not be, it's not like, it's roughly equal to, of order of magnitude, the individual, Chandra observations that we have, so,
It's really Poisson.
1,000-ish counts total.
yes, yeah, like 10,000, 100,000-ish counts.
100,000.
This is very high.
That's
Such a nice image.
How many pixels are there in this image?
Let's see, it should be, it's like, it looks roughly like 128 by 128 or something.
I have a quick question about the prior choice.
Mhm.
Why, usually when I look at this type of image reconstruction, naturally everything is sort of this convolution with the PSF, and so I always think naturally the problem sort of seems like it should be in frequency space, like you should be putting some prior on structure, which sort of suggests like maybe some type of Gaussian process or some type of like power on the Fourier transform. But instead you've chosen this sort of real space prior, and this sort of results where you end up with structures sort of at roughly, the size of the PSF, like it sort of gets evenly spaced by a PSF width. Is sort of a very common outcome, no matter how much regularization you put on. I was just curious if you've looked or thought about doing anything in either the sort of frequency or angular power domain, or instead of this sort of like patch-based domain.
No, we haven't considered that.
Well, not with Jolly Deco, but Lira does. I mean, it's not quite frequency space. Lira is another thing that. So
It's a version.
it's not a version, right? I mean, it's a completely
It's a different prior.
It's a different.
Yeah, it's a different prior. So, but it's based on, it's a digital prior. So effectively, it is looking at what the how much power there is in different scales and so on. So what the reason we actually focused on a real image spatial prior was because we realized with Lira that not having that is very limiting. We kept wanting to use the fact that there was something special about the image to take away that part and look at the structure. But your point is well taken that we could also be using a frequency filtering to get rid of anything that is smaller than the PSF.
Yeah, or I think usually I feel like it's sort of like around half the PSF width is sort of when you start becoming completely prior dominated.
But that's an interesting suggestion to look at the frequency space. We haven't done it, and I'm just wondering for for images like Cygnus A, where you have a lot of counts, maybe that's possibility for faint images. Like
Please get his paper out first.
Oh, yeah, sure.
Oh yeah. No, I know, but it's an interesting case to think about.
So I guess this reconstruction is the maximum a posteriori. It's like a gradient based.
Yes.
I would wonder how much stuff is going to change if you also consider uncertainty. So to me, this doesn't seem like one of the like the reconstruction doesn't seem like a sample from your prior, right? It's something like it's a weird thing. There were ducks in the whatever. So I would think that if you changed from one prior to another prior and you consider the uncertainties, let's say, you wouldn't get so much variation. So you would end up at different places within this kind of, let's say, credible pictures,
Mhm.
variable reconstructions of ducts. But like in general, all the pictures of ducts which are consistent with the observation would be kind of the same, mostly regardless of the prior, I would think. I mean, because this looks very data driven to me, doesn't look like a prior driven reconstruction,
Right,
just like the exact location of the maximum.
Mhm.
And there should be an easy way, so if you're already doing the gradient, you can just do a Laplace approximation to get like a very crude uncertainty estimate and check it already. Like it should be like computationally pretty straightforward.
I had a quick question, unless you wanted to respond.
I was
Sorry,
just
that was a
wondering
comment.
about uncertainty.
Okay.
No, thank you.
Is this- yeah. No.
Okay, so I've done this type of process, but for plasma physicists, and I just did a toy example, it's probably simpler. And one of the things that happened is as I increased the resolution of the image, I got more and more incorrect structure in my reconstruction, which I thought was bizarre, because you're in essence increasing your sample size, so. I was just-
Increase the resolution of the data, you mean?
Yeah, of the image, like
yeah.
make it more and more pixels. So I was just curious if you found that at all, or?
So we do something like that. It's like we will upsample our reconstruction to try to like, I guess, yeah, extract more information, right? There is a limit to it, and essentially, if you are upsampling, or if we upsample too far, what we get is that essentially the features in the prior need to be roughly the same size as the features in your actual image. And so if we upsample, right, we're saying, okay, the priors are now really small, like the patches are really, really small. And so we're looking for these really small features that we don't have statistics for, or like we don't have enough counts for. And so it ends up like getting too sharp again, or it gets sort of decomposes into point sources again. That's sort of what we've noticed.
So you could use your prior to try and fix that, but changing it,
We
or it wouldn't.
have not considered trying to like adjust the prior size, right?
Also, there is the natural limit to the resolution of the data, and it's a pixel size and maybe some pixel, but you have the uncertainty on the location of the events, which limits the resolution, so you cannot go too.
So what, were you using Poisson like count data?
Yeah, yeah.
So when you go higher resolution, was it the same counts, there were just fewer counts per pixel? So the same total count?
No, so you basically have your counts are increasing
Oh,
with the
okay. As you go
resolution.
higher
Yeah,
resolution,
so
you
it's
get more
still
data.
like same noise to
Yeah.
signal, it's just that the more pixels I put in, the more structure I
That is
got,
weird.
which was, it might have
Like
just.
not more unreal structure.
Yeah, which
So
I thought
real
was
structure, you'd be
bizarre.
happy.
Yeah, but it was like. Wasn't necessarily a robust method, so I was just curious if your method did better.
Right, yeah, no, our priors still need to be roughly equal in size to the structure in the image. Okay, so, okay. I wanted to mention that along the way of actually, I'll come back to this, sorry. So I wanted to introduce the object that I modeled, Cygnus A. We have a lot of data for Cygnus A, very well studied, over 500 kiloseconds of.
So you say, I'm sorry to interrupt, active galactic, it is our.
Yes,
active
yes.
Like
Yes.
this is our neighborhood black hole.
Yes.
No,
you mean-
it's no, this is in extra
Oh,
galactic
oh,
class.
yeah.
No.
Yeah, no.
Oh,
It's not,
yes.
not,
oh, this is not Cygnus.
not
Not
Saturday.
No, yeah.
Not
It's Cygnus.
It's fine,
Not
now.
I have misunderstood this the whole time.
It's-
So this is in a different galaxy.
Yes. Sorry. But what I was saying, yes, is that this is our like prototypical high energy or high energy AGN in the nearby or very radio loud
Yes.
AGN in the nearby universe.
Yeah, you know, redshift
Yeah.
is 0.0561, so it's far away from us.
It seems kind of small.
It is small compared to 4, okay?
Yeah, no,
Yeah, exactly. I don't know.
For some of us, that's local neighborhood.
Like
Well, for
red,
today, it's too
our
far.
black hole would be 0.001 or
Or
something.
even
No.
less.
No, so it'd be 0.0.
Oh, right.
10 kiloparts.
Hmm.
10.
Okay, never mind. Sorry to interrupt.
No worries. So very well studied object. We have, so there's two different instruments on Chandra. There's ASIS and HRC. HRC can essentially just a high level overview. HRC can slightly better sample the PSF.
HRC has no pixels.
Basically, yeah. You get less uncertainty on the position of your counts. And whereas ASIS has much better energy resolution. And so we have both instruments, much more ASIS than HRC. So most of my work has been focused on ASIS, but so it's also been well observed in other bands. So the top image I was showing radio in green and the Chandra observations in blue. Whereas below we have Hubble imaging on the left, and then we have JWST imaging on the right. And so also a curious question was whether or not we would find, when we deconvolve the images of Cygnus A, whether we would find Cygnus A2, which was believed to be transient in like around about half an arc second away, so about the size of the PSF. And so, which is about a kiloparsec away. We didn't know what it was. It's never been observed in X-ray. People have gone looking, had no detection. So we were curious if we could pick it out. Let's see.
So you're looking at this very small region down in the
Yes.
center. not
Yes.
The whole cluster.
Yeah.
Just very small square.
Yes. And so, as I mentioned earlier, or as was asked earlier, we get essentially a spectrum for free with Chandra. And so in Reynolds et al., they have modeled the different components of the AGN in the spectrum. And so you can, like, they've broken it down into like colder intercluster medium, a hot intercluster medium, and then reflection off of the dust in iron K alpha. And so what we can do is that we can break down our many ASIS observations into energy bins. And so we can model, or we can deconvolve just the softer component, the middle component, and the hard component. And you can sort of roughly isolate some of these, like these components, or at least have higher concentration of certain components in certain bands. And so essentially, just jumping into the results, we did this with Jolly Deco, and this is what we get. And so, yeah, these are scales, roughly like a couple kiloparsecs. In the soft band, we can see what we believe to be the wind from the intercluster medium sort of being blown out. It aligns with the jet axis, that sort of like bow tie shape. Whereas in the middle and hard bands, we're looking at the hotter ICM and the iron K alpha line. What was very curious to us is what's going on here. There's sort of these voids in the image. And we've spent a long time trying to figure out if that's real or if that's an artifact of our model. And so far, it's been very consistent. We've found those voids essentially like every way we've tried to tune the model. So make of that what you will, I suppose.
Actually, can I ask a question?
Yeah, of course.
Can you use the like different spectral bins together? Like it seems like if you were trying to decide between a diffuse emission and a point source, you know exactly how the PSF should evolve, given you have the spectrum and given you know how the PSF is different for each energy. So is there a way to use that information to kind of decide in the model between diffuse emission and structure, I guess?
Okay, so I suppose what you're asking is like, can we use the different energy bands to like jointly fit the like the output of the flux image reconstruction? The answer is not really, unfortunately, because we expect the structure to change with energy. We can model the PSF for each of the energy bands that we have. But if we, for example, try to jointly model the soft and the middle energies, you'd end up with sort of a blend of the two, which you can do. I've done the whole band, right? Like the whole response from Chanda, roughly half a kiloelectron volt to 7 kiloelectron volts. But you sort of end up with the composition of all three of these images.
I mean, you can imagine doing something like a pixel by pixel spectrum and that would be but that very smoothly across the image, the spectra. It'd be a whole nother model, like in another dimension, right?
I think this is something that was considered before, we just haven't gotten to it.
Yeah, also there is the limitation to the scale of your image in each energy, because you have number of counts per pixel, which limits the 3D analysis like that. But it will be interesting to do because this X-ray spectrum of Cygnus A region is very complex. So you have lines in the soft band as well, not only the one in this broadband image. All the spectral lines which are below 1 kV are lost because it smooths all those energies. So in Chandra you see these lines, and I think Zach earlier on was doing the images in neon and silicon lines. I think there were two lines we were looking at.
Yeah.
But this is still broad, so you separate some of these line structures and you can see the locations of the emission, which is interesting in this case, right? So that's the soft part. Overall, the choice of these bands was driven by, let's look at the soft emission, which is mostly, in this case, the wind of the electron scattering of the structures in the wind versus the jet and maybe the central region where we expect the ion line emission from the reflection as well. So, you can go narrow and narrow and see this.
Amanda, I should mention that there's a group at ESO Garching led by Fabio Acero, and I forget the person who actually did the work. They have something called blind source separation algorithm, where they do something that the kind of thing that you suggested. It's like treat the a spectrum associated with the diffuse components separate from point sources and see how they fit together.
Is it blind source algorithm?
Actually, we don't know if it's a point source.
Oh, but what was the algorithm?
What
was the algorithm called?
Blind source separation, that's what they call it.
How many counts, what are the counts per pixel in this image? What does 500 kiloseconds get you?
Well, you get roughly, maybe 10 counts per pixel in the sort of the greenish part. In the very center, you'll end up with 100 counts or 50 counts.
Yeah.
50 counts.
Per pixel, yeah.
Per pixel or per bin?
Probably per pixel or.
Yeah.
You can bin the ACES data at super resolution.
The sub-pixel.
Sub-pixel.
Yeah, so I think that's what Zach is.
Okay. So we have about 2 or 3 minutes, so.
Okay, no, go ahead. Yeah.
Oh, I have nothing to say, I'm just taking a short 3 minutes.
Yeah. Then go ahead.
Okay, I actually did want to share, I know I'm running out of time. I wanted to share something really cool that we sort of discovered on the way, or I discovered on the way. Which was that it turns out Jolly Deco is very good at registering X-ray observations. So we have 18 ACES observations. And I mean, typically for image registration, you would either take like the centroid of the emission, or you would take the highest counts pixel or something like that, and then you would use that to register your images. This Jolly Deco can actually also, like, at the same time as doing image deconvolution, it can also accept a shift of X and Y for each observation as it's jointly fitting. And so you end up with a maximum likelihood estimate of the positions of the images as well. And this does a rather good job of registering the images, and it's also point spread function aware. So like different roll angles of your observations, like since the point spread function is not necessarily axisymmetric, this method is aware that your counts are going to be blurred in different directions in different observations. And so yeah, I think I'm basically out of time.
And
So.
by the way, this answers, somebody was, Amanda perhaps, that,
Oh, yeah.
you know, there's 100 counts at the green level.
Oh, yeah, the plan.
Mhm.
Susan, are you gonna share slides?
I don't know if I have the Zoom.
Okay.
Oh, you don't have Zoom link.
I switched emails to Alaska from Los Alamos.
Oh, right.
I missed.
Or email it to us, we can.
What's your email? I can forward it right now.
Susan.s.glenn.
So if there are any more questions,
So one of the things Zach is working on now is trying to figure out that beta.
Yeah.
Using cross validation.
alright, and you can actually, you can see what design,
We can talk about it. We can
We can talk about it.
yeah, but no time.
And so it turned out that flexibility in the prior actually makes it harder, right? It'd be nice if we're just like.
Oh, no, it's fine.
So the work is ongoing.
Yeah. So as long as, while Susan's setting up, I have a question. Why, you know, I always look at this and I always go back to, why do we need to have these discrete models and do all these bins and stuff? Why not just say, let's just propose a continuous spatial model in XY. We have some function, we propose a continuous spatial model as a function of spectra. You know, you can have some, I don't know, let's just say conditional normalizing flow that produces some density map across the image, changes as a function of the spectral intensity, and you evaluate the Poisson, you know, point process exactly as you would normally. You know, you can put on any priors you want, it's in function space, you can do any resolution you want, you can use any sort of, you can register every single photon hit, you don't need to do any binning. What prevents us from doing this?
Computational cost.
I think it's cheaper.
Really?
Yeah,
I mean, we have a,
because you can exploit all the standard tricks of machine learning. You can
So
do
how do you-
patch training and
How would you define this continuous function?
normalizing flow.
Okay, this is where you go.
Yeah, for the intensity.
I mean, you have some non-negativity constraints on that object, which.
Well, you
is
just
hard to
model in,
sample.
you just model in log or softmax or something if you want non-negativity. Negativity.
It's a new way of thinking about it. There was no normalizing flows 29 years ago.
Well, Zach is not even 29 years old.
Yeah.
You didn't blame that on Zach.
Yeah.
Josh, it's a very, very nice, new idea, so.
Yeah. Now I'm just wondering if there was like some other constraints that prevented like the thinking in function space.
no, we have.
No.
It's always, my dream has been to do a completely
Like the probability.
Nice,
observer.
so,
Yeah,
yeah.
For the
Set position.
For the model.
For the data.
The data.
Data are already,
You can have unbinning data.
we are binning it now to.
Yeah.
To force it.
But there's
There's
still native binning in certain
That's
It has finite resolution though.
Okay.
So there's a point where it doesn't make a
Yeah.
difference.
Yes.
The systematic start taking.
No, but,
Yeah, yeah,
but Josh.
Okay, oops.
Would you be fine with like a spline interpolation? That's like a function thing. Okay, well, they're doing that, but with linear interpolation and lots of grid points, I guess. So you can indeed decrease the grid and put some splines. And that's gonna give you a
Yeah.
little bit of regularization, and also
Yeah.
Josh is gonna be really happy, well, almost happy.
Happy.
But
Well, that is, yeah, this
it's
is.
not.
And that's not too hard.
Yeah.
You know what I mean?
Yeah.
Yeah.
To regulate it though. But let's move on, because we're already taking up time from Susan. So take it away.
So this is work from my postdoc, and it actually Zach did a great job of setting up the data. So it is basically a way to have an image, and you have an object you're interested in that image, and you want to kind of estimate the underlying shape. So the shape of the object in the, unnoisy, unblurry space. I'm gonna go through this really quickly. It's for fusion. So this is plasma physics, where they take this capsule and they compress it uniformly, and then they get an implosion. And they wanted a way to kind of estimate, based on an implosion shot, how close was I to achieving fusion. And so it's really the uniformity that we're gonna look at, because we're just really asking how symmetric was my implosion. And so it's a very similar setup where I have my implosion, I have neutrons coming off the source and hitting a detection plane. And if you have 20 pinholes in your aperture, you'll kind of end up with 20 realizations of your source, and they're blurry and noisy images. And there's this complicated reconstruction, well, not super complicated, Zach just described it. We're using the simple reconstruction process that the plasma physicists use. I was not brought in to fix that at all. I was brought in to use the final image. And so this method, it is generalizable to other types of data, but essentially all you need is underlying space. So ours is the implosion shot. You have some object in that space like the source, and you want to understand some geometric information of it. So in our case, that would be symmetry. And then you end up with your data images, and they have this reconstruction process. And so I end up with, if I have 6 pinholes, I would have 6 image estimates of the source. And then I can average them to get a sample mean image. There's also another way to do it, but I'm just going to use this because it's the simplest. And then you need a way to bootstrap.
So these are separate images?
Yep. So
Can you superpose them?
yeah, so basically, Los Alamos does it where they do the reconstruction with all the images at once. So they have some big PSF function, and then Livermore does it where it does each of them separately. And so it's just Poisson counts, you're doing the EM algorithm, and you just have a stopping criteria. And
No,
that's
I mean, how do you do the vertical registration? How do you-
Oh, so we actually, you don't need to really, I guess you do need to care about it when you're getting the sample mean image, but I can't speak too much to how they do that beyond what I already said.
I mean, do they just maybe just take the mean and stack them?
They do a lot of kind of eyeballing.
Oh.
They look at the residuals, and they see like, are the residuals structured in the truth, and if they are.
Sorry. It's me trying to join.
Oh, okay. And so they throw out any pinhole that you have some kind of structure in your residuals, and
Are they open to other approaches?
definitely.
You came in saying, I was brought in not to do this bit, but maybe there's not.
Fix this process. So I think, there's definitely potential to use your method for this process. So here's another kind of data setup, which is very different, where you have some density. This is an annulus, so it has some kind of complex geometric structure, and you just sample points from your density. And so your data is points, and then you can use a kernel density estimate to estimate the density.
Sorry.
And then
It's like
It is?
What?
Why?
Oh, the
It looks like that data.
There's no like scatter.
And even the dots
Yeah,
are.
that's a good point. So I actually just sampled from a unit. But I should have sampled from the density to get there. That's a good point.
She gets exactly.
I was confused, maybe you have like a mask, which is like.
No, yeah.
Well, see if she solved it.
Yeah,
Yeah, we
With
can,
the-
So-
see if she solves it.
Yeah.
Okay.
So I
We
mean,
have this
this.
problem with a supernova 1987 ring that looks very
like
like this.
Oh, okay.
And we've spent probably about 10 years, not full time, occasionally trying to figure out if those little glumps are real. Or if they're just.
Is why I wanted to do this today.
Okay.
So, and then you end up with you can bootstrap points, right? Cause I've just sampled them my ID and I can get bootstrapped kernel density estimates. So this is a very common setup in topological data analysis, but we can use it in this more geometric data analysis approach. Okay,
So you believe, so you have a beautiful circle, is that just because that's how you simulate, or are you really interested in structures like that?
it can be any kind of structure. As in my examples, I'm working with, you're gonna get a contour and you need a closed curve, but
Okay.
you can do this process with surfaces.
Yeah,
I
but it
just
can be a
haven't done
pretty
it.
irregular.
Oh, yeah,
closed
yeah,
curve.
yeah, you can have any kind of,
Yeah.
as long as you are not changing the topology
Yeah,
of your
yeah,
curve, essentially. Okay, so anytime you're interested in kind of global structures in an image, that's when you might wanna use statistical shape analysis. Lots of times, I would say don't use it, but if you are interested in kind of this global structure, you have complex patterns, it can be pretty useful. And working with the entire image is difficult, and so typically you're gonna get some type of representation of the object you're interested in, and then you can try and understand the geometry of that simpler representation. And so I have my image, my sample mean image, and I have my true image, and then I can get just the simplest way to get a representation is get a percentile contour. So I look at the pixels, I get a percentile, and then all the pixels in that percentile become part of my contour, and it's just this ordered set of points. And so now the question becomes, well, I want to know how symmetric is the true contour, right? This contour in red. And so I would want to know, well, how symmetric is the contour of my data, and then what will that tell me about the true contour? And a very maybe like common, a very like common traditional statistical approach would be I'm going to fit a shape to my contour, get the best possible fit, and look at the parameters. But that's not really the question we're trying to ask. I'm not asking if this is a circle, what's its radius? I'm asking, is this a circle? And so geometric data analysis, statistical shape analysis techniques are going to say, I'm going to look at a distance between two shapes. So I'm going to say, how far away is my estimated contour from a circle? If they're really close, maybe the true thing is a circle. If they're really far away, maybe it's not a circle. And so a very naive way to get a distance between two shapes is the L2 distance. And so any people who've worked with registration would know if you're just gonna, you have an ordered set of points, if you're just matching points and moving around your curve, and then you get the Euclidean distance, your distance between two curves is gonna be bigger than 0, even if I have the exact same shape. And so there is information in the embedding that I'm taking into account in my distance that I don't want to be a part of my distance measurement. And then I also have this issue where some curves have more points on them than others. And so what does the matching become? So statistical shape analysis is saying I'm going to get a distance between two curves. Yeah.
So if you have a model circle that you're trying to ask whether it's whatever shape that you have is a circle, how do you put points on it?
So it actually doesn't matter how I place the points because I'm gonna remove any differences due to sampling between two shapes in my distance function, basically. I'm gonna remove, so basically these 4 shape preserving transformations I'm gonna remove. You're talking about parameterization, which is just sampling essentially. So you could generate a circle of 100 points and you could generate a triangle with 50 points and you could have uniform sampling on your circle, non-uniform sampling on your triangle, and my distance is gonna try and remove any differences due to how I'm sampling my points. Yeah. So statistical shape analysis removes the first 3 shape preserving transformations. So that's gonna be any difference due to location, rotation, and size I'm gonna remove from my distance. And that also helps because I don't have to register anything. The distance measures take that into account, so I don't have to do any pre-processing. And then elastic shape analysis gets rid of this fourth thing, which is parameterization. And that's just sampling, and it's a very complicated definition. It's like the speed a particle moves around the curve, but it's really just sampling. And that is actually the most powerful part of this whole analysis, is that I can compare curves, surfaces, or functions that are on different coordinate systems, images with different resolutions, and I just don't even have to worry about that with my distance metric. So the way people get this distance is quite complicated. It gets into differential geometry. I had not taken a differential geometry class when I was trying to learn this, and I've only been learning it for a year and a half, so I'm gonna do my best. But essentially, here I have two curves. They're both hourglasses, and they're the exact same shape. And so when you're getting these distances and you want to remove parameterization, you want to make your distance invariant to reparameterization or sampling, the main way to do it is using something called an elastic metric. And so when you're using an elastic metric, you're getting into Riemannian geometry, and so you're going to be using geodesic distances. And that's because the elastic metric, if I have two shapes, it's going to give me a zero distance for common reparameterizations. And so that's why that's why we're getting into differential geometry essentially. And so the square root velocity function is what's gonna help me compute things easier. So that's why people do this transformation. So they take their two curves in R2, they do this square root velocity function transformation, and with the elastic metric, you end up on the unit Hilbert sphere. And the reason why I care about that is geodesic distances are defined, they're unique, I know things about them. And the nice thing about this square root velocity function transformation is you're using the derivative of your curve, which doesn't depend on location. So I've kind of taken out location. You can also add a constraint if you want to center your curves. And then it also kind of has this constraint to scale to be the same. So I've removed differences due to scale and location, but I still have differences due to rotation and parameterization. And so then people essentially put things in equivalence classes. So it's going to be the elastic metric, and you're gonna mod out differences due to rotation and reparameterization, where you essentially have your reference curve, which we'll say is the red hourglass, and then I have my blue hourglass, and I'm just rotating, reparameterizing, getting a distance. Rotate, reparameterize, get a distance, and minimize it. Find the minimal rotation and reparameterization for my distance. And so that's how I find that the distance between these two is 0. And really intuitively what this distance is giving me is it's telling me the optimal deformation of one curve into another curve. So it's telling me how quickly can I go from hourglass to question mark curve, and how much energy did it take to do that? And so that's intuitively what the distance is giving you. When you're in curved spaces, statistics becomes really difficult. What's a probability distribution when you're in a curved space? There is a way actually to get an average curve. So if I give you a ton of curves, you can get an average curve. There's also a way to do shape PCA, which I think is really cool, where you can say, what's kind of the dominant shape changes happening between my curves. And a lot of that is going into the tangent space, but we're not going to do that in this talk. So, but I just think it's cool. So now we get to finally my method, where we have these contours. We're interested in the true contour. I have my sample, and I have this way to get distances between curves. So how can I do statistics? So as I said, it's really difficult to do statistics in this space, and that's why we have this interesting setup where we're essentially going to assume you know the true contour of the source, and I had multiple data realizations of it. I could do these transformations and get an empirical distribution in blue, and then I could build a confidence region for that empirical distribution. And we're using the fact that we are starting out with sample mean images to get the correct asymptotic scaling there. So that's how we can, basically we can assume that our distribution is non-trivial. And then I don't know the true contour of the source. I only have one sample mean contour. And so we're going to use our bootstraps where my data becomes my truth and my bootstrapped contours become new realizations of my data. And then I get this red bootstrap distribution. And assuming I have the same asymptotic scaling, things converge in distribution, then I can say that I can use my bootstrap distribution to approximate the whatever Z alpha is. If your alpha is 0.05, the 95th percentile. So this doesn't fully happen because you're going.
So when you say bootstrap, how do we do this bootstrap?
Yeah, so when you bootstrap, you are doing the image. So you take let's say I have 6 pinhole images and I've reconstructed them. You can sample from them with replacement and get, a new sample mean image. That's
just getting counts.
Yes, but that's assuming no spatial correlation. It's assuming you know the true PSF, which we don't. There are ways to adjust for that if you're scared that you have non-IID data. But for now, we're just gonna assume that we have those constraints. And you definitely have that for the points in space, right?
I think you do it with like a parametric bootstrap as well.
Yeah, I think you could try something like that. What the physicists do is they sample a smaller number without called subsampling, and it's a way to bootstrap when you have non-IID data, which I had never read about until talking to them. So there are ways to try and adjust for that. But yeah, we're essentially going from image to contour to square root velocity function to elastic shape distance. So I have 4 kind of functional transformations I'm applying to my image. And so as every time you do that, you have to check and see, well, how did that affect my bootstrap? And the issue really comes with the elastic shape distance, because I'm minimizing essentially the L2 distance. And so I have no guarantee of a unique solution in my optimization. And then the L2 distance is non-differentiable at 0. And so you kind of have this push up in your bootstrap distribution. So our confidence intervals are conservative, which if we're going to be wrong, we want to be wrong in this direction. There is I have another example. So if your images are smoother, this is with the kernel density, you're gonna have better alignment in your bootstrap distributions. And that's just because if you have a smoother image, you're more likely to have differentiability in your function when you're going from image to contour. But if you don't have, you have very noisy images, you can do this M out of N bootstrap to try and pick a better asymptotic scaling that you have stability essentially in your bootstrap distribution. And so there's kind of like extrapolation based ways to figure it out, or you can, just do this simulation where you start at, let's say I have 100 pinholes. So my sample size is 100. I could just look and make my asymptotic scaling root 100, root 90, root 80, and I can see how my distribution of elastic shape distances is changing. And once you kind of hit a plateau, that's what you pick for your new asymptotic scaling. And so I would just say if you have very smooth images, lower sample sizes, you probably don't need to do this adjustment. But I would always recommend trying to do some kind of simulation to see how your specific data is falling into this interesting way of doing inference. Okay, so once I have a confidence interval, I can do a hypothesis test where I'm going to say, I think the null shape is a circle. I think the null shape is a square, whatever you want it to be. And then you can use your empirical bootstrap distribution, and then your test statistic is going to be the contour, the sample mean contour and your null contour you've picked. And you can see, is my test statistic in the confidence interval of distances, or is it outside of it? So I did a power analysis where I generated a bunch of data from a source that is circular and sensitive the test is. So we know our confidence intervals are conservative. So, at what point am I able to even detect, no, I don't think this shape generated the data. So we know the data is a circle. So I took a circle and I slowly indented it. And that was the easiest kind of shape difference for the test to be able to pick up. Because it's a real asymmetry, or I guess it's a bigger asymmetry. Taking a circle and smushing it into an ellipse was kind of harder. And then it was also, the polygons were really weird. So I took a polygon and I increased the number of sides. And it looks okay now, but certain multiples of 10, the test really struggled with. And part of that is when you're doing this process, you basically have your reference curve and you have your data curve, and you can pick how many points you want to be on both of them when you're getting your distance, and it's going to kind of interpolate if so I think it just struggles. The code's a little buggy with certain things.
And if you're linearly interpolating, it might start looking like a higher order polygon.
Yeah, exactly. But the other issue with the code, I'll just say if anyone wants to use this, is that some curves are going clockwise and some are going counterclockwise, right? And the code tries to pick which direction to go, and it doesn't necessarily do a good job. So if you start getting bimodal distributions in your elastic shape distance, that just means half of your contours are going clockwise and half are going counter. And so I just got rid of that in the source code. I commented out the part that does that. And this is on GitHub where I describe how to do that. And then I just made everything clockwise to try and get around that. That's another thing.
So I noticed at one point you had this hourglass.
Yeah.
So that means that you're insensitive to process.
I know, I thought that was interesting too, because I thought that was, a change in topology, right? To go from an hourglass to, let's say, a circle. But my mentor, who this was his thesis, he said it's okay as long as you have a closed curve. It should be able to do this.
But you're always going to have a closed curve, right? Because at
Well,
any point you can come back.
So a big issue is let's say I'm at the 95th percentile for my contour. In some images, you're gonna have two separate clumps. And then what if I'm comparing it to an image where I have one clump? If I'm getting a distance between two things, I need one curve. So the minute I start having two curves that I want to compare to one curve.
Contours of a bimodal thing would be geometric topologically. Different than contours of a unimodal thing.
Yeah, and I believe there are ways to work with it, even if you do have that difference in topology where you have bimodal and unimodal. It's just a more newer area people have worked.
So since there's only 4 or 5 minutes, maybe we can think about what this, bring it back to the imaging.
Yes.
The idea is that you would have a contour, you're finding the uncertainty on the contour of the image.
Yeah.
And that would be quite interesting to you.
Oh, yeah.
You can do it with surfaces too. I just personally haven't. And you can also do it with trees even. You can kind of.
You're making it more complicated.
Sorry.
I'm trying to do with the 3-minute image.
Yeah,
So that would be for a genealogical tree or
Yes.
not for for the evolution of species.
Yeah.
Evolution of languages. They have
Yeah,
these
yeah,
trees,
yeah,
that kind of
yeah.
stuff. But
So, Sue and I talked about this briefly, and I was like, there's gotta be some kind of astro examples that would be interesting to think about with this. So I wanted.
Yeah. So it reminds me a little bit about those projects with Thomas. Remember there were they were closed curves.
All the boundary analysis things.
For the
that we were doing.
jets, yeah, we were
All
doing
the
jets.
KD paper on boundary.
on the judge.
So that's right, so because there's this kind of history of semi-successful attempts. There is a history, there's a bunch of maybe examples that you could kind of look at kind of immediately.
Yeah, so maybe like we can follow up, I'll send an email to everyone and.
Yeah,
So Katie was trying to find the actual boundary, which is a little less defined actually to me.
Yeah.
Whereas a contour is a little clearer.
Yeah, yeah,
A boundary is kind of like, it's like where does it end, right?
yeah.
No, but what's her name, Joy.
Yeah, that's what, yeah, that's.
Was working on trying to find segment the data and find suitable.
Right, and she was segmenting based on the density, so it's a little different problem, right? It was like a Poisson process and like where is it dense and where is it less dense? But a lot of because it was astronomy, right, they turned out to be looking like contours, right? Because it was a source, it was denser than the.
Right.
So that was continuous data.
That was continuous.
So that makes it a little bit cleaner. I mean, because when it's pixelized, the contours also are
Yeah.
like strange, right? You know.
I would go back to Spillover 87 and see if there is a way to determine whether this.
But although her picture looked like that, it doesn't
It's
look like
not
her
this-
method is really designed for deciding if there's
I was
close.
just trying to understand whether you know, like if you do your bootstrap, you know, how often do you get those
So the issue,
enhancements, for example?
the issue
Yeah,
is there's
yeah.
optical images that have these clumps.
Right,
And so when we looked at the X-ray image and we thought we saw the same clumps, that was a
Yeah.
big finding. The
right,
problem is that when we reinitiated the algorithm, all the clumps moved around.
right.
So
Not
they
not all the clubs.
Some of them stay.
enough of the clumps to make us worry.
Yeah.
I think you could care about like more local things because that's when you're getting into more of like these tangent spaces where I'm just wiggling or moving around one part of the surface and trying to see maybe if it's real by how much I can wiggle it with, I guess, if I have some way to get uncertainty in it. And so, and I think when you're doing that, like if I'm just at one point of the curve, I think you can maybe assume normality potentially, like it's a lot easier to do statistics if you're just looking at local.
And you have point spread functions in there.
So these are, you mean like these real data is generated by having a point spread function and having noise and then removing it.
Cause we'd like to know where the contours are not in the data, but
Yeah,
in the.
but in the-
image,
yeah.
the Source.
Yeah.
So, and do you use, is it like a Poisson likelihood?
Yes.
Cause you were talking about EM. so
Yeah,
that could
yeah,
fit in,
yeah.
right,
I believe they use Poisson, I think
If
sometimes.
it's EM, it probably
Gaussian.
is, that's where that, you had mentioned EM. that
Yeah,
algorithm-
yeah.
That algorithm, that's what he was calling Richardson-Lucy.
Yes,
It's the
yes,
same
yes, yeah, yeah.
algorithm.
They have a more complicated version of it though, so I don't wanna say anything.
Yeah, it's,
Right,
but more in broad,
yeah, more
broad
or less,
strokes, and that data that the supernova,
Yeah.
it's relatively low count data.
Yeah.
Can you think of the photon locations as essentially continuous? So that might be a nice one to start with. I mean, it would be, maybe not start with, maybe a different one, because then it is also a complicated contour because of all these little, it's like a bejeweled necklace, right, with all these.
yeah,
you know.
so we're working on extending this at the lab to when you have like multiple little clumps that
Yeah.
you wanna, instead of just one beautiful curve,
Yeah.
so.
We can use EO 102 from the Jolly-Decker paper.
That would be an easier place to start, yeah, absolutely. Don't start with a complicated.
Yeah.
Yeah, we have other ones, yeah.
Okay, we're over time again.
Okay.
Sorry. So the next set of talks are a little bit more neural networky. Image analysis, neural networky, and then everything else is the general organization for today. So next up, Samantha.
Is there a Zoom link that I?
Oh, okay, so you can show now.
I've been here the entire time, what are you talking about?
No, we did the introduction.
I've been here for the last 9 years.
Oh,
Yes.
Hiding.
we did the introduction of everybody.
Everybody knows.
Yeah.
The Zoom link was in the email that you sent.
Yes, it should be in your Astrostat announce CHASC thing.
It's also on the top of the agenda, as far as I remember.
Isn't it at the top of the agenda?
It is a link to it.
Okay.
Yeah.
Oh, I didn't mean like the first thing on the agenda.
It's towards the top.
Got it. Yes, got it.
You want to share your screen?
Full charge. I don't know. Are you at full charge? Yes. Could I borrow your charger for a few minutes? Thank you. Oh. Okay.
Well, for people who don't know me, I'm Casey Mandela at Cambridge, England. I used to be here.
And somebody else came in the back. Do you want to introduce yourself?
Yeah, hi. I'm Rocco. I'm a pre-doc student. I work in Astro AI. Have background in stats. I was interested in this.
Here at the CFA or?
Yeah, this year.
Excellent. So you push the cookies towards David, somebody.
I was trying to make that less awkward.
Do we cookies those?
Multiple.
These are only. A lot of people don't like
You can't have that one to Josh. You know, the one that fell off the.
Anyone wants?
You guys don't want cookies? You say yes or no? No, it's just me.
Can you push that?
That's not real raisin. These are in its own.
Sorry, David.
I was chasing them. Oh, sorry. Let's push it back.
Oh, wait, seeing this.
Oh, right, sorry.
Oh,
I should presume break somewhere in there.
Break up.
Okay, everyone's favorite, FBI.
I want you to be
With galaxies and giant suns. So you want to take it away? This little introduction?
Oh, that looks very much like our AI generated image.
Oh, yeah.
Probably
Probably not real.
Like ChatGPT.
That's it. I was gonna say, yeah.
I was saying.
It was either that or Nano Banana.
Okay, go ahead.
Right.
So I will be presenting an idea of how to make the embedding driven simulation based inference more interpretable. I'm not sure if this idea is going to work or not because I still have to try it. Yeah. So yeah, it's called disentangling posterior sparse autoencoders for embedding driven simulation based inference. So as I mentioned, I'm working with another advisor and she is working in bioinformatics and we are working with sparse autoencoders and transcoders for interpretability of protein sequences. So yeah, it worked for that part. So that's why I thought that probably I can try it here as well.
Can you just tell us what it means for posteriors to be entangled?
Oh yeah, so for that, I have the next slide. So this is my JSON poster.
I have to reshare if you're only sharing one part of your screen.
Or you can just go through your slides. You don't have to like answer my question. Maybe you're comfortable.
So this is the JSM poster for this year. So we were trying to actually use like a scalable inference method, which is simulation-based inference for our work. And I was mostly generating LSST type observed data to actually check the posterior distribution out of it. And as you can see, I was I was trying to like compare nested sampling Vecchia approximation with simulation based inference, but for like for the Vecchia and for nested sampling, both they could capture the cross correlation function between bands. That's I was generating 3 live band data. But
Sorry, just to quickly,
yeah.
so Vecchia approximation is like a sparse Gaussian process approximation that's being applied to lots of this stuff, just trying to make sure we're on the same page.
Oh
Yeah, because I can see it on the poster, but there's a lot of text.
oh yeah. So the thing with nested sampling and Vecchia approximation is they could actually get what is going on with the can you see it now? It's
Yeah, that's good. Mm-hmm.
Yeah. Okay. So it's the row which is the fourth
Row.
yeah, fourth row, the cross correlation function for both nested sampling, it's far more better than Vecchia. But for simulation based inference, it's like absurd. It was not getting any signal.
So what can you just say, what does better mean?
Oh, so the prior I was taking out the true value for row, it was like 0.9 between bands 1 and 2 and 2 and 3. So it is giving around.
Would it help if you came over and pointed? Because I'm not sure about.
Or use your mouse, yeah, I can't even read what the numbers per row are, actually, it's a little too blurry.
And you're trying to say that the middle thing is just way too bigger than the other two.
Well, it's clearly bigger, but bigger might not be bad.
No, but nested sampling is like standard, gold standard one.
SBI was taking mostly, so my prior was set to 0.6 and 1, and it was taking the like mean of uniform distribution. But for nested sampling, it took 0.88. The high peak was at 0.88, and my true value was like 0.9. But also for like sigma f using nested sampling and using simulation based inference, so sigma should be right skewed, and it is right skewed there, but as you can see, it's like.
So do you have a reason for believing nested sampling though? I don't understand. Just because it's more established?
Yeah, it's like standard.
Yeah. Well, standard thing can be wrong. I mean, not every. No, just in general.
Yeah.
Oh yeah, because
I'll tell John Skilling right away, I'll be like.
because we also tried Dynasty, and it also gave like same thing.
Dynasty can be wrong too.
But if you get multiple things giving the same answer, that's an indication.
Yeah, but Vecchia was also giving the same thing. So
Similar.
yeah, like at least like right.
Yeah. I mean, the Vecchia is quite a bit wider than nested sampling. It's
Yeah,
kind of
for
halfway in between, really.
Yeah, but for like sigma f, they are like pretty similar. I believe my Vecchia.
Which one is sigma? That's the second row.
Yeah, this.
They look quite a bit alike.
What was the sampler for the Vecchia approximation?
Like
The Vecchia approximation, it approximates like the joint density, but you
Yep.
would still need to like
Yep.
explore the posterior.
Mhm.
So is it like nested sampling with the Vecchia approximation, or
Oh
is it a
yeah,
different
yeah.
algorithm?
It's,
that
yeah,
operates?
it's nested.
Okay, so same method, just
Yeah.
one with approximate, one with.
Yeah.
So it makes sense that those two would agree then.
Yeah,
Yes.
yeah.
Sorry, so what are the parameters you're fitting for? Are they
Oh.
the hyperparameters of the GP kernel and mean, or is it something else?
They are just hyperparameter for GP kernel.
Okay,
Yeah.
and how are you, now that we've established using nested sampling on the exact likelihood, you're using Vecchia, you're using nested sampling, the Vecchia approximation likelihood.
Yeah.
Now, what does, specifically, how are you doing the simulation-based inference?
Oh, okay. So for simulation based inference, I was simulating using the like GP covariance function. So the simulator has idea of what GP covariance function is for our case. And then I was just training it using the neural network and passing it through the masked autoregressive flow.
Right, but I think Casey's asking, so for SVI, you need to construct these data model pairs. So the model, if you're simulating from the same model, then
Yeah.
everything is great. But what's the specific data? Are you passing in like the raw time series, some summary of the time series?
It's just simulated data, which was based on that passing through the
Even the sample
simulated.
time series?
Yeah, so that is the LSST observed data that we got using the latent function. Okay, so it's so FT, our latent function follows GP mean and covariance function that we have, and from that we are actually generating observed data, which are like independent observed data, and they have like XT, comma all the like errors which are measurement errors. So that was our observed data.
And so how large is that vector that's being passed through?
600 cross 4.
Okay, so essentially your neural network is being trained on a 600 cross 4
Yeah.
input. And when you
Yeah.
feed it into the neural network architecture, is
Yeah.
that is there any sort of like embedding or pre-processing of that data that's done, or is it just directly into normalizing
No,
flow?
it's the embedding size was 128.
Okay.
I should like probably small. Yeah, so 128, and my embedding was like mean and max pool. So that's a specific type of embedding. So I'm taking mean and also I'm taking max of that particular mean.
Is that done directly on the data, or is that done post like some, simple, fully connected layers? Or
No, it's directly on the first it is actually transforming the 4 inputs to the 64 output, like it's just scalar transforming it in the transformer, and then I was getting the embedding from those 64.
So, the reason that I'm asking, I think that Casey's also asking, is that
Yeah.
if your embedding of the data is too simple, then you actually are like throwing away tons of information. And so your summary statistics that you can use for SBI would essentially be handicapping the method substantially.
Reducing the information.
Yeah, you'd be dramatically removing like tons of information. And so it might not be a surprise that using SBI you actually don't do very well. But that wouldn't be a statement about SBI. That'd be a statement about how you've done the embedding of your inputs. Yeah, that's why I think we're both asking some questions about this.
Yeah, thanks for completing all my thoughts for me.
Sorry. Do you, did you have more you wanted to add as well, or?
Well, I guess, you're giving the presentation, so I was interested in the sparse autoencoder aspect of what you were proposing, which is the main thing in your plan.
But yeah, for the embedding part, I think I am just using I'm giving transformer those 4 inputs in manifold, and it is like scalar projecting it to the 64 dimension, and then I was getting 64 plus 64 because I am doing both global mean and max. That's why it's 128. So I was getting embedding based on those 4 particular inputs. So now that's a good question, and I'm not sure that if I'm making a mistake or not while actually getting the embedding.
Something to look at, right?
Uh-huh.
So you use something similar, you were saying, in a biostatistics or
Yeah.
application. Did you have simpler data? Like
No,
a lower dimensional data?
No. For that case, we use usually pre-trained models, which are like ESM, ESM2, or
So somebody else's model.
Yes. Yeah.
And here you had to develop your own model.
No, it's simulation-based inference is also someone else's model.
I see. So it could be, there was 2 someone else's presumably. One of them may have been more sophisticated than the other. Yeah.
Yeah.
So what is the light curve? Like, what is the astrophysical source of the light curve? What kind of object is it that's
Yeah.
Okay, so I was generating 3 light bands. So we don't have any actual data. We are just generating light curves, and it is LSST type light curves.
What
So,
does
yeah.
that mean? Like, were they, what kind of sources they were? Like quasars or galaxies?
Yeah, I
or
think it's
stars?
quasars. Yeah.
So is it generated for stamped random walk?
Yeah. No, it's based on squared exponential kernel for my practice as of now.
Sorry if I missed something, but I'm not sure what it meant by entangled posteriors.
Okay, so the thing is, I was trying to, so I have more pages. But yeah, right now I can't compare, like as of now, good enough or giving me like good interpretable posterior. So I believe
So
that.
so you wanna like compare the posteriors that you get under different.
Yeah. Yeah, so I believe my embeddings are missing something, and I want to use sparse autoencoder to actually make it interpretable and see if how my raw inputs are connected with my embedding and what my embedding is trying to say me, so that I can finally check.
Do you really only have 4 parameters? Cause then, you could, you could do something to see what the real posterior is.
11 parameters actually, yeah.
Yeah, 11 is different than 4.
Yeah. Yeah. So it's like, oh, okay. So 3 bands. So 3 different bands have 3 length scale, L1, L2, L3, and then 3 sigma Fs, and then 2 rows, and also 3 mu's.
Yeah.
But I just,
So, so if you just had one band, right, you have you're saying that the data is a realization of a Gaussian process that sampled at particular times plus probably some measurement error, right? So then you have maybe 4 parameters. You have a mean function, which maybe you're saying is constant, right? Okay, so then you have a amplitude of the kernel, which is telling you the variance, right? Then you have, okay, this is 3. Then you have the length scale, which is really a time scale.
Yeah.
So that's 3.
Yeah, it's not 4.
Right. So without using an autoencoder or a transformer, like I can tell you a summary statistic which will get you the mean.
Yeah,
You just calculate the mean of sample mean of the data. And the amplitude is really just you can take the once you have an estimate of the mean, you can take the standard variance, and that's a good estimate of that.
Yeah.
And then as far as the timescale goes, it has to do with how long does it take for a fluctuation in the curve to go back to the mean and then fluctuate like that. So that can be estimated from the autocorrelation function.
Yeah.
So these are interpretable statistics, right?
We tried that.
Okay.
And then we tried also using SBI to check.
What happened when you tried what Casey suggested?
Okay, so that one was actually easier. Even SBI couldn't also understand what is going on with that as well. So something is going on with while I am actually giving it the data and trying to get the posterior estimation out of it.
So I don't understand. When you did that, what did these pictures look like?
Like what do you mean?
When you use a simple sample summary statistic, you could use that with SBI.
Yeah.
And what happened?
And it was also like very much noisy. It was not
too big.
Yeah, it was very flexible. It was not giving anything that we wanted, like sigma F to be right skewed, or it can actually predict the L properly for the posterior sample, but for the like sigma F, it was not that good. So we were actually having sigma F problem, like amplitude problem for the very first.
And if you because you're using simulated data, part of the hard part is estimating the kernel for GPs. If your time span is too short, then it's hard to estimate, say, the length scale.
Yeah.
But if you just, since you're simulating, you just simulate a time series that's 10 times longer, make sure you have lots and lots of data. Did that improve things or did it make it worse?
No, I tried with, so if you are asking about the time scale, our time scale is of 800 days. So it is like, I haven't increased after that. So I should check that. And also.
The time span of your data set is 800 days?
Yeah.
But when you simulate a true length scale, really time scale in your kernel, what is that number?
So it was like 1500.
Oh. Yeah. Okay, so usually you would need the time scale to be a lot longer. Sorry, you need your time series to be a lot longer than your time scale to estimate it properly.
Okay.
So that's probably
the problem.
Something you should, if you're simulating the data, you can simulate it for the next 100 years if you want.
Oh, okay.
I mean, not for you spending 100 years. I mean, you can do it on a computer.
Yeah.
Sorry, I want to clarify. So you said that you have 3 bands, but are you modeling them independently?
The 3 bands?
Yeah.
Yeah, they are independent. Yeah,
So
but
you
they-
could like explore like the posterior for each of
Yeah,
them
yeah.
separately, so then
Yeah.
it's only three
Yes.
dimensions, not
Yes.
like.
And also, but the row is actually saying how they are related with each other, like how they're flowing, bands. So that's why we have cross correlation
Okay.
in between bands. Yeah.
Okay, so.
So I guess I have a question on so you mentioned you're thinking about using these sparse autoencoders for interpretability here.
Yeah.
So in general, like these sparse autoencoder methods and structures are designed sort of with a couple strong assumptions about you're doing unsupervised things, you don't quite know what you're looking for, so you impose this sparsity constraint over a very, very large, complicated network where you have, many, many things, and you have like this humongous latent space you're trying to condense down. In this problem, though, you actually know sort of what the parameters you're recovering are.
Yeah.
And you know a lot of these tools for what the structure should look like. And you have lots of hypotheses or experiments where you can test this, either from the data side or from the model side.
Yeah.
So have you thought about using like simpler tools? Because sparse autoencoders are kind of known for being a little finicky. Something like linear probes or very simple like gradient-based, analyses or like ablation analyses or any sort of like much easier interpretability methods for these models?
So we haven't tried because it's just I'm still working on it. So the idea that of using sparse autoencoder just came because of that project. It's not so that's why, but that's a good suggestion. We can actually try that. Yeah, thank you so much.
Yeah, it just seems like using a jackhammer to like approach a problem that might just benefit from like a regular hammer.
Yeah. So actually that's the I just wanted to actually present this idea to get the feedback from you all so that I can probably improve and do something actually can be done with this.
So I would recommend it's more on the data side. If you're working with simulated data, just generate a ton of data so you're in the large sample limit relative to your model and parameters. And then, in large sample limit, you're supposed to get the right answer if you have a good model and a good statistics. So
but also like is it efficient to simulate like more data or generate more data using the simulator, because it's also like expensive?
I mean, generating 8,000 days of quasar data from a Gaussian process was fast. Shouldn't be hard, yeah. I think that's easy.
Okay.
Because you only have to calculate that covariance matrix once.
Yeah, that's true.
The hard part is when you're varying the parameters, you have to calculate the covariance matrix for different parameters.
Yeah,
That's where
the
you-
inverse.
Yeah, that's where you have to do the Benchix approximation or something complex.
Yeah. Okay, then I will also try to probably increase my simulators. So that's the idea. I had more slides, but it's more about how to use sparse autoencoders in this. But okay, I'll just try simpler method to make it probably more interpretable.
Anything else?
I was gonna say, if you haven't tried it, I mean, one of the amazing things about any of these like SBI or neural net frameworks is that you have a lot of flexibility with the model being fully differentiable. And you can, of course, change what you're differentiating with respect to. So, of course, like the default is you differentiate with respect to the weights. You can do like updates and train the model. When the model's done, you can absolutely differentiate with respect to the data or with respect to the parameters for SBI. So if you have some posterior that you get out of some, object, you can definitely compute like the gradient and exactly like how sensitive it is. And, you can get like the Fisher, type of thing. You can compute a Hessian. You can do all sorts of stuff to figure out exactly how sensitive it is to small changes in the parameters or how that will change the, constraints you get. You can do it with the data. You can see how sensitive you are to different amounts of the inputs. So there's an amazing set of stuff you can do without having to reach for any new tools, just with the model that you have. I think that would be great for generating lots of intuition for what may be going right and what may be going wrong.
Yeah, okay.
Should we move on to Lishan?
Thank you. Thank you so much for your feedback.
Yeah. Millions of galaxies.
I'm sure.
James.
I'm gonna email to all of them.
Yeah, it's interesting.
What's your name? Oh, Susan Glenn?
Yes.
Oh, nice to meet you briefly.
Looking here for the introduction, you would have.
You know how expensive that hotel was? I wanted to make sure to milk every last minute of that.
Oh, wait, see, you can go out this way.
Oh,
If you prefer.
yeah, this is great.
I'm gonna ask.
Oh,
I didn't want to ask. Okay.
David, or cases back.
Yes, one with the broken zippers.
Last term who actually was really interested in like lots of interpretability methods for time series data. So I'm gonna send you like the report he wrote up, which does like a lot of these gradient based analyses and trains a bunch of different neural networks on like random time series.
Oh, that's
that's-
Send that to me too.
Can
I'm-
you-
I'm-
can you-
Sure.
Can you upload it?
Sure. Yeah, sure, I'll send it to the turn. Well, I didn't really.
Oh, actually,
Oh,
you know,
it's interesting.
I'm gonna make a web page for this workshop. So send me all your presentations too.
Or presentations, but that's not,
Yeah.
this is the.
And any additional info.
But that would be nice.
Are you at 7237 at PSU? Okay, I'll forward it to you and also to Casey then.
And me,
Okay, and then
Yeah,
uh,
I started.
thanks.
Okay, Lishana, you ready?
So I did a similar presentation yesterday at GSM. So I think for this talk, I'm gonna give more details for the model and how we did some calibrations. And so this project is about doing STD, Galaxy STD fitting using an SBI. Yes, and then my collaborators are Joe, Olivia, and Elijah. They are astronomers who help develop and maintain the Prospector, which is also a very popular Galaxy STD fitting tool. So I think everyone knows what photometry is. So I'll just give the introduction here. And then once we get this raw photometry, we want to obtain galaxy parameters, and in astronomy, people use this SCD fitting tool. So you have some values of the galaxy parameters, and you use the forward model to generate the synthetic spectrum, and you take some integrals to get the synthetic photometry. So the goal is to find parameters such that your simulated photometry is most consistent with the observed photometry. So you can see here, yeah.
So is it only photometry that you're using? There are no spectra involved anywhere?
So only photometry, because our Sheila catalog is a photometric catalog, but we have HATEX as kind of like they share overlapping sky coverage. So for some sources, they do have the spectrum and we can get spectroscopic redshift from it. But the Sheila catalog actually contain much more sources. Yeah. So here we can see that we have these observed photometry, these green points, and then we have synthetic photometry, these purple points, and we're trying to see whether they are close enough, and this distance is characterized by the chi-square. So you can see that we need to generate a lot of the spectrum and do comparisons. When we do SCD fitting, the typical time for generating spectrum is 15 to 20 milliseconds, but you have to do this many times, and a lot of people are trying to make it more efficient, for example, by using the emulator.
So
yeah.
Chi-square of 10 means like 3 sigma or
I think so. This is actually just
No,
an illustration, not how you.
Oh, it's not like a real data.
No,
set.
it's more like a better illustration to actually see it. But this paper does use Prospector.
I was wondering, I mean, one of my main questions was gonna be, is it a good model? Because if the residuals are so gigantic, I'm wondering like,
so
are they working in totally like misspecified?
So the forward model here, the power factor model is actually a physics model, like it's purely driven by first principle physics and it contains a lot of parameters, unlike EASY, which was like the one that we later do benchmark that they use template galaxies. So you can think of prospector with FSPS as a purely physically driven model that is quite accurate and widely accepted in astronomy, I think.
What is your sample, like what's the redshift range that you're looking at and what
I
like
will
photometry?
talk about
And then, sorry,
a little bit
didn't-
later. Yeah, but so the parameters we want to infer are these galaxy property parameters, but on top of these parameter, redshift is the one actually we're most interested with, and spectroscopic redshifts are very expensive, so we're trying to get good photometric redshift estimates. And you can see that this is a inference problem. So traditionally, prospector incorporated dynasty. So thanks to Josh, who developed this nested sampling algorithm. And for each single galaxy, it takes about 20 to 48 hours to get the full posterior distributions of galaxy parameters. So here we're seeing, for example, stellar mass, star formation rate. So this time varies because we can specify how good the posterior is by, for example, increase the number of light points, and there are some specific hyperparameters you can tune for nested sampling. It works really well and it is very accurate. This is also a likelihood-based method to do galaxy inference, but with the advance of technologies and large telescopes, we're just able to observe much more galaxies than 10 years ago. So we want to develop a faster algorithm to do Bayesian inference. So the goal of our work is to do fast inference with accurate redshift estimation, and we want to scale it to the full Sheila plus CATEX catalog, and the method is to use a simulation-based inference. So I also want to discuss Sheila plus CATEX. So Sheila is a photometric catalog, whereas CATEX is a spectroscopic survey. So Sheila has about 4.44 million photometric sources, and among these, there's about 16K sources that has spectrum, and we are able to get spectroscopic redshifts from it. And we think this is really good to do SED fitting. Of course, when we do inference, we not only get redshift, but other galaxy parameters, but at least for one of them, we are able to validate with the spectroscopic redshift, which is like the true redshift that we think of. And then another important thing we want to do is to study cosmic web, because Olivia, my collaborator, she is very interested in cosmic web. However, in order to study this, you need to know the redshift of all these sources. So we want to get a good redshift estimate for them, for these like 4.44 million sources. So that gave you like a 3D location of where these galaxies are, so that you can study the structure of the universe. And then, and another thing I want to mention is Sheila survey is actually divided into 7 tiles. And each tile has different depths and different detection limit. So when we fit these SBI models, we fit them tile by tile because the detected object in each tile is different. So the detection limit tells you how bright an object needs to be in order to be considered as like a legit object rather than a background noise. So in total, we fit 14 SBI models, 2 for each tile. One model is using the complete photometry, so we receive no missing data. The other SBI model is fitted with using partially missing photometry with some masking strategy. So The simulation-based method, I think everyone knows this very well. We need two things. The first is parameters, and here our prior is the physically motivated informed prior, developed by Bingjie Wang, I think 3 years ago. We also call this like the prospector beta prior, and it is driven by the correlation between redshift, stellar mass, and star formation history parameters. The observations are generated through the simulator, which is prospector with FSPS. And as I mentioned, we think that this is a very physical model, and it has been studied a very long time in astronomy. And after we get parameters and observations, we send it to SBI and we use the normalizing flow. But specifically, we find that neural spline flow is better at capturing the complicated multimodal posteriors compared to the more common masked autoregressive flow. We actually did a lot of tests with this, and we think that this works better. However, using neural spline flow as a density estimator does make the training to be longer. So comparing using the masked autoregressive flow, which takes about like 10 to 20 hours, the neural spline flow takes about 20 to 50 hours during the SPI training.
So can I just ask, so you have an F, so you're doing simulate likelihood free, but you it's because of the computation. You do have a likelihood if you wanted to use it. Is that right?
So when we use the nested sampling, we do know the likelihood, so there is no problem with it, but we
want to
just want to scale it.
Yeah, exactly.
Yes.
Just to make sure I understand. And then for you, did you had to deal with the same issue, presumably, to take the data and summarize it through your neural network?
So actually, our data is not that high dimensional, so we do not. I try to do an embedding, but we tune all these parameters and embedding parameters using Optuna, but we don't find any substantial differences. I will list all the parameters we have and all the observations we have, but it seems that embedding is not necessary.
What's the dimension of the data?
I can
just
do it
roughly. Is it like a
For photometry only, I think it's not huge.
Is it
It's not huge. So the galaxy parameters
Yeah,
are
32.
17 parameters, and the features are photometric measurements. 16 photometric band and another 16 correspond to their uncertainty measurement.
Just very quickly on what David was asking. In the mass sampling, you don't account in any way for the detectability of the source, right? Whereas with the SPI, you technically account for detectability. So that may be a little bit of a.
You can make a better model.
Yeah,
essentially, you could put more.
Well, I guess
You
they have
you can work in the detectability into the likelihood.
in the likelihood, yeah. But
Yeah.
I doubt that
Yeah.
it's already in the.
Yeah, I talked to Josh yesterday about the detectability things.
I guess here you're using some very simple, like a signal to noise ratio cutoff or something like that when you
Yes,
simulate.
so Sheila actually posts the detection limit.
I see.
So the detection limit for all of them. However, the detection criteria is these photometric band that I highlighted here in green. So if an object is brighter than any of these, the object within this band is brighter than any of these 4 photometric band, you consider this as detected.
And I guess you have a little bit of problems with mass sampling if there's some missing bands or.
Correct. That's why we kind of fit 2 models. Additionally, we also find that if you trained with partially missing data, obviously we do a realistic masking. So the missing pattern is based on the Sheila catalog, and about 2/3 of the Sheila catalog has partially missing photometry. So when you're doing the masking, essentially you have like 1/3 with complete data and 2/3 with missing, like partially missing.
So when it's missing, why would it be missing? Like if it's missing, is that an indicator that it was dim, or could it have been missed just because they didn't want it?
So these situations both happen. So sometimes you don't have a sky coverage. So for example, in Tau 7, we do not have YHSC. But sometimes it's just because it's dim and we're not really sure. And also the original catalog is in the flux and we have some negative flux. And this is the reason why when we do error model, we convert it to our standard magnitude because we're trying to keep these very thin objects. So, okay, let me go back. So we use the normalizing flow and so the main motivation for us to do this is because we want it to be much faster than before. So for our work, we kind of divide it into the 4 stages. The first one is to generate synthetic photometry. And this is with the prospector beta framework that takes about 4,400 CPU hours, and we do 100 core parallelization, so we can actually finish this within 2 days. And then after we get the simulated photometry, we perform the detection limit, and that leaves about 6 million. So the detection percentage is about 6 to 7%, depending on the tile. And we do a training set and testing set split. And we use the neural spine flow under this NPE to train, and this takes about 20 to 50 hours. And then we do model diagnostics and validation on the testing set, and also on the spectroscopic redshift we reserve from the Hatex. And the main diagnostic we do is like SBC and SBC for like marginal distributions as well. We have done like KS test, for like coverage check, all the stuff. And then we do this for about 50K objects, and this takes an hour on GPU. And then after we did some tuning with the model, we test on the Sheila catalog and compare our predicted redshift with the spectroscopic redshift. And we did this for 160K detected objects for Sheila, and this takes about 3 hours on GPU. And I want to mention here that this framework is repeated for every single tile. So you do this 7 times.
So why does it take 3 hours? I mean, one sample is usually some kind of milliseconds.
Yes.
I would expect it to take 5 minutes or something.
No, it's actually not that fast. I have a speed comparison later. So I think it takes, I didn't do
Okay, well, here, okay.
the math here, but it's not that fast.
I think it also depends on how this is being batched or thrown in. I mean, if you're
That's
if
correct.
this is essentially running in a for loop where you're going through every object, running it through SBI and then getting a bunch of samples out, then I could easily see how this could take this long. But if you're doing like large batch computations, feeding it through like SBI, getting some huge things out and like some giant matrix that fills memory, I think this could be much faster.
That's correct.
Yeah.
Yes, but additionally, I think neuron spine flow is faster compared to the mask autoregressive flow in terms of posterior sampling after training. This is just by the construction of the flow.
Yeah, I definitely think that, you know, if we're comparing like, I forget how many like CPU, GPU hours compared to this, like difference between like 3 hours and 6 hours is pretty small compared to like a gajillion years.
Yes, so honestly, I would say that the major time is spent in generating the synthetic data through the simulator and also the SBI training part. And for this simulating process, we actually tried the emulator, but it doesn't quite work. So we're doing with the more traditional prospector.
Interesting. Why would it work? Sorry.
So I'm not an
Are you
expert.
using just announcing speculator emulator or?
So actually Elijah, which is also my collaborator here, I think he developed emulator for his other project, and we just want to try to see if it works. But I think it doesn't, so that's why we didn't use it in the end.
There is one by just announcing, it's called speculator. That to me work.
Okay, we can I can double check. We will be sharing the script for doing the training sense that contain an emulator version. So I can go back and check. So another thing we encounter is when we have the synthetic photometry, we need to assign an uncertainty. If your data has really good quality, people just use Gaussian. I think that's what I saw from many papers. But the Sheila catalog actually does not have a really good quality of the data, and we find very noisy and heteroscedastic data, and some of them are just extremely faint with very high uncertainty. So what we do is if we want to assign uncertainty for an object with magnitude at 25, we go to this tiny magnitude bin, and within this bin, you will have a uncertainty distribution, and we just fit parametric distributions to characterize this error distribution. So in the end, the uncertainty is a random sample from the best fitted distribution. And I have people ask me why not to do non-parametric. So first of all, these distributions are oftentimes just almost all the time unimodal scale distributions, and actually the parametric fit is pretty fast. We just use AIC as the criteria to select the best fit, and it works very well in practice. Any questions? Yeah, and I mentioned that the model training contain these parameters, and also some of the parameters are very well constrained, and we know this by the physics. However, there are some parameters which I believe is the AGM parameters and some dust parameters. They can only be loosely constrained by the model. So the parameters of our top interest are redshift, stellar mass, and stellar metallicity, and there are some like more nuisance parameters. Yeah.
Good question. So I just noticed that you have 16 bands.
Yes.
And 17 parameters.
Correct.
And you're going dealing with the overspecification by adding the uncertainty as extra features.
Yes.
Why should that work? Because uncertainties should not be informative about what the parameter values are.
I do think uncertainty is necessary. It tells you how certain.
No, it helps you estimate and
figure
out this.
But it does provide information about your estimates. So if you have very large uncertainty for every single photometric measurement, then SPI wouldn't actually be able to learn.
There's actually technically a kind of sneaky correlation with uncertainties as well. If you imagine like your luminosity function, you have some survey, or like you have some sample fainter sources, like they'll be further away, lower mass. So there is actually some slight correlation there. I remember an infamous example was this was like for photometric redshifts back in the day. They used some random forest and they fed in the bands and the uncertainties, and they showed that like the highest informative feature was like the G-band mag error. And I was like, well, that's just because it's a proxy for the G-band magnitude, because those things just go.
Why wasn't the G-band magnitude the most important?
Because when you have extremely correlated features in a random forest, it can pick those out randomly. Yeah, not very robust. It's like a known issue if you have very correlated inputs. But like, so I think there is actually potentially some information in the uncertainties separate from the parameter just because it proxies like the population.
But it's still a duplicate of the magnitude.
If you were doing just parameter estimation, but if you're trying to estimate, full SPI, Li-Shen is, I think, correct. That's very important.
So I guess that is my real question. Why is it that the SPI can work when, if you try to do this with as a regular fit,
it's the magic of machine learning.
It's expectation value versus distribution, right?
But there will be a necessary. Both will be very important. So that's fine. We're fine with degeneracies and correlations. Well, we're fine with fitting 17 parameters to 16.
With 16 data.
That issue is a general feature of modern neural networks.
Well,
there's a lot of parameters inside of these things, right? More than just your science parameters, right?
That is true, but those just get recycled and don't actually come out of that.
Yeah.
So I mean, these are, but this is literally, I mean, you're writing the likelihood. But
So the other thing that exists there is this very structured prior that Vishwan mentioned, the prospector beta, which actually has it has been constructed from a lot of observations to constrain very few parameters, which are global parameters of the population. So that is something which also, if it goes in the opposite direction of the degeneracy between the parameters, can actually break it. So that's one of the things, and it does really help. So I think that if you train on alpha, like the whole, you get way worse results. That was the point of the paper from 2023. That if you use this prior, you can get way better.
Yes. That's correct. But also I want to say that not all the 17 parameters are very well constrained. So for example, like dust ratio and AGM parameters, they're basically returning prior because they're just like so loosely constrained. I think AGM parameters in some very specific case, maybe in the high stellar mass case, they can be constrained and get some information. And SBI is so good at capturing these specific patterns, but I think for a lot of the dust parameters, we're just not learning anything, and also for some star formation history parameters, we're not learning anything. But it's still too good to have an estimate, even though it's dominated by prior, because if you get the values of these parameters and you get some posterior samples, you can convert it to star formation rate, specific star formation rate. So that will still be something useful. But I would say that the parameters that gets the best recovery is definitely stellar mass, the redshift, stellar mass, the dust 2, which is the dust optical depth, I think. And stellar metallicity also get a good recovery. However, it has a lot of noise, so it has a lot of scatter.
Just very quickly, in your architecture, you have all of them jointly.
Yeah.
Have you tried also doing marginally redshift to see if you get better results?
What do you mean marginally?
Just train normalizing flow in one dimension for just the redshift. You should get, if everything works out, you should get exactly the same result as taking the 17-dimensional normalizing flow and marginalize, like sampling and then throwing away everything else. But usually if it's like a network which targets just one thing, it will work better because the embedding can embed it better.
Something we tried, it's not exactly the same, is we tried to put redshift as a fixed parameter, so we are not interested in inferring anymore if we have spectroscopy redshift already. So then redshift, so here is on the left, we put it on the right as a fixed feature. Yes, observable. It does improve the performance of models slightly because, for example, redshift and stellar mass are highly correlated. And if you get a wrong redshift estimate, then your stellar mass is probably going to be very wrong. So that will improve. However, for those good redshift estimates we got, then they are just all correct. So it's either they're correct at the same time or they're just all wrong. And then something I want to share is the redshift prediction. And here we are comparing with the spec Z, the truth, and we do EZ as a benchmark. So EZ is a very popular photometric estimator. Of course, it not only predict redshift, it also predict other galaxy parameters, but it seems that it's particularly good at predicting redshift. So we find that our method is comparable with EZ, and we actually have slightly better metric, for example, NMAT, outlier fraction, and bias. So this object that I'm doing prediction is a low Z object from HATEX, and they are primarily very bright objects with very well constrained photometry. So actually for HATEX, you either have low Z object or a high Z object due to the design of the survey. So we have more low Z object than high Z object, and I think high Z is Z greater than 1.8, and you have very sparse objects in between. And additionally, we think that EZ produce more catastrophic errors. For example, here at this lower left, severe underpredictions of EZ. And additionally, I want to say that underpredictions are probably not driven by prior, because our prior is the general prior we assign for redshift marginally is has a median around 0.8. So this is actually in the low Z setting compared to our prior.
So do you know why those large differences, large errors are in the lower? Do you understand how the catastrophic errors in SBI case are?
So I actually know that for EZ, a lot of these are happening because EZ take the mode as from the posterior, and a lot of mode appear at very they have a very sharp mode and then some less dominated mode at the tail. So that's where these happens. And for SBI, it has some underprediction here, but we think that what we find is maybe there's some degeneracy between parameters, because what we find in our method is usually SBI, EZ, and nested sampling would fail in exact same pattern in the sense that they produce similar redshift that is all wrong in the same way, like all of them underpredicting or all of them overpredicting.
Are there error bars?
There are error bars, but I'm not showing it here.
Yeah, but are they big enough?
They do. So SBI is very conservative. So if you can see here, we do comparisons with nested sampling. I would say that we do find nested sampling produce much narrower, not much narrower, like slightly narrower credible intervals, as well as the contours you can see here. SBI is in general much more conservative, and we also did coverage check.
But it's the same model.
Yes.
You're not doing anything different. You're not adding, because there's things you could do with SBI that are dealing with missing data and stuff like that. You're not doing that. It's the same posterior.
So right now, this is the same posterior.
So one of them is not giving you the right answer, or maybe.
Yes,
that's what often happens.
That's why I was talking to Josh yesterday. So we think that, for example, maybe we don't have enough good quality sample from the nested sampling. So we want to, for example, increase the number of live points. So what we find is that actually nested sampling and SBI produce very consistent point estimate. However, their posteriors are just not identical. And a lot of times SBI is being conservative, whereas nested sampling is being overconfident.
So this is real data, right?
Yes.
Okay. So they may both.
Yes, so actually here, we fit 200.
Yeah.
Very
Because one of them has Monte Carlo approximation problems
Yeah,
and then the other one is like smoothing, so.
Yeah, so you can see that actually here we compare with SpecZ, so these are all real data from the Sheila catalog. However, due to the limitation of computation, we only do for 200 samples for nested sampling.
And at the end of the day, actually, if you get error bars that for these ones where you kind of know the truth that are reasonable, it doesn't really matter. You know what I mean? Because the posterior, you're not a principled Bayesian. I mean, maybe you will. If you want error bars that cover screws.
Yeah. I mean, here you can see that on the right, even SBI is very wrong. So SBI gets the SpecZ, but in a less dominated mode, but it's still within the one sigma range of the complete interval. It's just barely guessing.
We're running out of time.
Yeah.
Okay.
But I mean, it's supposed to finish at quarter after. Are there any other questions or anything else that you wanted to say quickly, or?
Well, maybe just one quick question is, so I'm seeing some difference in these methods. Any suggestions to see which one is more correct? Yeah, they're more correct, I thought.
Well, I mean, one of them is correct, I mean, not necessarily, I mean, if you're a Bayesian, the posterior distribution is the posterior distribution, and it is defined, and you wanna approximate it, and if your algorithm is giving you the wrong thing, it's a problem with the algorithm. If you are if you're more like using a Bayesian, you're really trying to get good coverage, then it doesn't really matter, as long as your algorithm, you can demonstrate gives you good coverage. Whether or not it's exactly the posterior distribution is less important. And I suspect it's the latter case here. So, I mean, you could imagine in the previous plot where you have that scatter plot, if you had, you kind of have error bars here.
Yes.
It's maybe still hard to tell. But if you could kind of somehow quantify the coverage.
Yeah, we did.
And if it gives you coverage that
That's
you're over covering.
yes.
Well, that's okay.
Yeah, you know what that's Park said.
Yeah.
Yes, I think there's actually a postdoc here at CFA named Anya Nugent who has been working on applying like Nessa sampling cross-spectral fits and comparing to them to like an SPI version called SPI++.
Oh, it's I think BJ's.
Oh yeah, he's on he or she is
So
on the
she
eighth
was
call.
also
And
in
I'm the
Joel's
lab
group.
author.
Yeah.
No, Ben Margolin is the.
Wait, sorry, which one?
No, SPI++.
Called Franken Blast, there's like,
Oh, this is the application of SPI++.
yes, I'm
Yeah,
looking at the
yeah,
application paper which is called Fracking Blast. Lead author is Anya Nugent, the second one is Ashley Villar. And in the appendix, they actually do a comparison very similar to yours, except these are for supernova host galaxies. And one of the conclusions, if I recall from the conversation, is that the SPI version actually seems to be more stable than the Nessa sampling version.
More stable.
Yeah.
Yeah, I think it's just a more stable approximator than I think Monte Carlo noise can be large. People underestimate how large this can be.
Very good. Shall we take a break? So we never really talked about lunch, but I guess we'll go to one of those places and
Yeah,
maybe people can bring the lunch back here.
Yeah, I mean, they will come here.